Okay, so some announcement before we enter into the content. The readings, the discussion that was to be held on Piazza, notice like there are only 2 or 3 entries right now. So please continue that, and that's due end of day tomorrow. So whatever readings I see at that point, the grade for the readings for the week would be based on that. So I'll mention the exact deadlines at the end of the lecture as well. But readings will be due, the discussion on readings on Piazza is due tomorrow. Today I'll be continuing more from the process of machine learning that I was discussing on Tuesday. I'll be going over the same ML pipeline today, but we already covered gathering data and extracting features in the last lecture. So if you have any questions around that, we can discuss, but then we'll move on to the next 3. Developing model, training and optimization, and evaluation. And then we'll go over a real data set and see how this can be performed using Python. Okay, so the process, as I described earlier, is that given a problem, you first need to gather certain kind of data and pre-process it and basically get the essential components of data that are needed to build a machine learning model on top of it. And then the data by itself is just not ready to just be pushed into a model. So after the data is prepared, you need to extract features out of it, which can follow a process of text feature extraction, numerical features, date time, in images. The image has its own set of features. So it can be any kind of feature extraction, but that's one of the largest component of this pipeline because you spend more and more time in building features. If you're using neural networks, you are providing some representation of the data in a certain limited way. And then you are training the neural net to learn more features. So maybe you're not doing full-on feature extraction manually, but your model will do it. Still, you have to prepare the data for the model to understand. So that remains as one important step. Third, I did go over it in the end, but I'll go over it again, is developing the model, because this is, again, one of the most important components. You know what the data set is. You have extracted certain kind of features, and now you want to use one of the many available algorithms to actually train a model, train on the data set, and find out sort of a learning solution. What is the process of developing a model in general? So we want to learn a certain function, which we believe represents the input and output, the link between the input and the output. We assume that there is some distribution from which, if we pull the sample, that is a good representation of how the data looks like, and we want to estimate that. We want to reach to that conclusion. We want to learn a certain relation between the kind of data that we see and the kind of outputs that it leads to, and can we actually learn that? So this is the core process where several algorithms have been built. There are different algorithms which are tried, but there is nothing which is known to work best for all the cases. But once you have practiced enough, you sort of get a sense that given a problem where the data looks somewhat like this, I think this is the family of algorithms that I'll start with. So essentially what you're doing is y is equal to wx plus b. That's just a simple function where y is the output of a model, x is the input, and w and b are parameters of your model. So this model can be summarized to be just a set of parameters consisting of w and b. These are the unknown parameters at the beginning, but you have a lot of x and y pairs. Data comes in, it has a certain output. If you are following the supervised learning process, you have a lot of x, y pairs. Using those, can you learn good enough values of w and b? That's the idea going into the process of a very basic model, right? You need to learn what are the best approximations of w and b that conform with the data and generalize it further. So one thing is to look at your training data and have a good accuracy on top of that. But another thing is to be able to generalize enough that if you're given new data, you still have a good accuracy. So you're not learning your training data itself, you're learning a general feature on top of the data, using the data to learn a model, right? The complexity of these models can vary. So there is something called like a single layer model. So you must have heard of names like linear regression, logistic regression. These are very small models. You provide a feature to them, and they perform one level of calculation on top of them, and that's the model. The model is very simple. Then comes the space of deep learning, where this complexity can keep on increasing because now you have multi-layer uh, models, and the number of layers depending on the complexity of data, complexity of the problem can keep on increasing. So ResNet is one of the most famous image classification neural networks. So it uses something called convolutional neural nets. We'll cover them when we cover neural nets, but that's a kind of learning module. And it has up to 150 layers. So it has different variants which use lesser number of layers, but 150 layers of convolution. One layer of convolution itself is quite an expensive operation, and then you have 150 of those. So these are just, and they are not the biggest deep learning models. Deep learning models can be really huge. So that is the scope from very single layer models which work really well on a large number of data sets to extremely complex models which are trying to learn object detection, image classification, natural language. The complexity. And the terminology of layers, I'll explain it more when I go in the neural net space, but assume it this way that each layer is a function, right? You take in your data, you apply a function on top of it, and you get some values. For logistic regression, when you do this, the values that you're obtaining after applying a function are the final result. But when we have a multi-layer module, those values are feeding in as the input to the second layer going forward. So that's the deep learning architecture. And each model would require some methods of training. The training follows there are several learning algorithms which are used with different models. But how do you really select a model? So that is one of the, I mean, after enough practice, it's not that difficult of a step, but entering into the process, it's a question where you apply your intuition, looking at the data, looking at the problem, you get a sense of what kind of classifier, what kind of a learner would be able to deal with this data, right? If your data is extremely complex, maybe logistic regression is not the way to go. Whereas in several cases, if you have a large number of features well defined, logistic regression mostly gives you a good enough result. So once you have practiced enough with different models and different data sets, different kind of problems, you develop sort of an intuition. But in general, there are these families of models that you will use. So if you have image data and you don't have features surrounding the image, no one has performed, let's say, a thorough feature extraction process on the image, and you have a lot of data, convolutional neural nets are good at that because they can learn the features from the images, and you can just build sort of an end-to-end architecture. But that's one example. There's no fixed answer. But the process in which you work with this is that you select a model, you train your data set on the model, evaluate the performance, and then you start to reason, okay, the performance was extremely bad. It's worse than the sort of random probability baseline. Looking at any data set, if let's say you're solving a binary classification problem, right? An input comes in and your answer has to be 1 or 0. If that is your problem, you have a 50% probability of saying 1 or 0. Or let's say your data has a certain distribution within itself, that 20% of the data set looks like 1, 80% of your data set looks like 0. So if I just randomly pick something, I do have 80% accuracy because I can just always say it's 0, and 80% of the times I'll be right, which means no learning, but 80% accuracy. So the model did not really learn anything. So your base becomes 80%. You have to sort of be better than that because without learning anything, you're just going in that direction. So this is a reasoning that comes with practice, that there are some heuristics that you will, just drawing this distribution of the data set is one. You sort of understand that you don't want to bias your learner too much, right? You will probably control this ratio. If your learning algorithm in the presence of this 80 to 20% distribution can never really learn something good, you will start to hide some data or maybe duplicate some data, augment it. But those are things that take place later on in the process. The approach is that a model can only prove its worth once you train and evaluate on top of it, and then you start to discover how is it. Some common examples of algorithms that are used: decision trees and naive Bayes. These are simplest algorithms, and they are taught generally in the first, second weeks of most ML classes. So it's good to know them. It's good to use them whenever they work really well because they're really fast. But they have their own limitations. I mean, they cannot learn a lot more complex problems. Support vector machines were one of the most famous ones for a long, long time. Then when neural nets came back into the picture, they started losing their popularity in a certain way, but still they work really well. Again, they're fast. Support vector machines have an advantage that even though mostly they work as a binary classifier on a straightforward feature data set, you can perform an approach of defining kernels where your feature data set can represent a more complex data. So I won't go into SVM. I mean, that's already covered in the ML classes, I think, here. But it's still a very powerful algorithm and fast. So if your SVM works really well, it's great for a problem. So there's no need to really apply just neural networks everywhere. Linear regression, logistic regression, neural networks. These go more along the line of algorithms where you have the y is equal to wx plus b, the equation that I showed, that kind of relation. That in linear regression, that literally is the answer, that you are predicting by doing a wx plus b. You are sort of predicting your value. And in logistic regression, it's one more step on top of that. You're applying a logistic operator, which is called a sigmoid function. The details of these algorithms, I'm not planning to cover them in the class, but I will. I've already linked to a set of ML crash course by Google, which contains a lot of the important stuff. It contains from linear regression onwards. And then I will also link to, there's a package called scikit-learn, which is good for things up till neural networks. So if you're not dealing with neural networks and all the other simpler learning algorithms, scikit-learn works really well. And it's easy to understand. It follows sort of a simpler syntax. So no matter which algorithm you're using, the syntax would almost be the same. So it's clean in a way to work with it. It's good for practice, and on toy data set, it's good to use. Going into neural networks, this will be the large architecture that we'll be dealing with most of the time. Current, like since 2012, neural networks have been extensively used in different. For images, they are the state of the art. For neural machine translation, neural networks define the state of the art. Object detection, and for many, many problems in vision, in natural language processing, in structured data, neural nets are being heavily used. They have some constraints around the size, the complexity, the requirement, the computation requirement. But with GPUs, with lower costs of GPU, with more cloud GPUs. So NVIDIA itself has hosted a cloud with GPUs. Google is hosting on Google Cloud. You can access GPUs. So basically, you're just paying for the usage, which reduces the cost drastically once you have to use it. And for practice, at least while using our UCSC account, we do have access to the Collab notebooks. I think even outside we have, but at least from UCSC, we definitely have that, which means you will launch a Python notebook, Jupyter notebook, on your Google Drive, and it will be running on a hosted environment. So you don't really have to do anything. It's already running on a virtual machine in Google Cloud with one GPU access. And that GPU is powerful enough to really build. I mean, you can build somewhat complex models. It has, I think, 11 GB memory, which is good to run larger use cases. And that availability is there. So neural networks, trying out neural networks, using them for small problems, even for larger problems, is very much practical now. The other thing in developing models is hyperparameters. Does anyone know what hyperparameters are already and would like to define? I mean, I can explain it with the other thing, but some of you have already used different learning algorithms, right? So do you know what hyperparameters are? I mean, when you're training those algorithms, is it an important space, first of all? If it is, then what is it exactly? I think any points that you have around it. Has anyone trained a logistic regression function? A neural network? Yeah. So can you think of some hyperparameters in neural networks?
I mean, similar to what you've written there, and anything that I had to change in my experiments have been a number of layers of features. Learning rate I've not worked with much, but sometimes having cascading the number or the number of features per layer throughout.
Right.
Starting with feed, it's
the number of hidden features, right? And you have observed the difference?
I think personally, I wasn't able to understand the exact ways in which all of these affect. Like in some cases, when okay, now it's improving, so we'll use that. It's not improving, we'll use something.
Right. Yeah. So the process that you went through is called hyperparameter tuning. There's no there's no standard approach for hyperparameter tuning. There are several tools that people have built, including me for myself, that sort of try to automate this process, and you use some logic, some intuition. There is no clear definition of this, but in reality, in real deployment, this becomes one of the most important steps. You have a model using, let's say, some first of all, what are hyperparameters? You selected the model. Now this model needs some variables. There are some variables associated with it, which are not the learned variables, which are the variables of definition. So you are building a neural network, right? Let's go even simpler. You're building a logistic regression model, right? It will have a size of feature vectors, right? It's going to do a sigmoid on top of wx plus b. Remember? So the x is a vector, and the vector has to have a certain size. There are a certain number of features. So that is the first thing you need to know. You cannot just say, okay, apply logistic regression without any information. That's one piece of information that you're giving to your model, right? But that's it. That's the piece of information you use in logistic regression. Now understand neural networks. That you have one layer, but you have another layer on top of it, and then you have your final layer. So you knew that, okay, I will go over this complexity using my Python example. But the idea is that there are some variables associated with the definition of the model. Some models are very simple and they may not need more stuff, but as they start becoming complex, the variance that are possible is huge. So you want to select some parameters to control that space, to fix some values that, okay, then the model begins. It is this big, not this big, just the size control, which is the number of hidden features, and number of layers is sort of vertically how big it is. And these things will play a role when your data set size changes. If you have a very small data set and you say, I've heard that deep learning models work, let me build like a 10-layer model. It's deep, it should be able to learn, but you don't have enough data to train so many parameters. How will you do that? Because a larger hyperparameters control the number of parameters. Parameters are what the model is going to learn, right? The variables that are ultimately at the end of a training process, the thing that you're left with are the parameters, learned values, learned floating point numbers associated with different weights and biases of your model. That is the thing that you're going to learn in the entire process. To do that, you use data, right? But to define sort of a fixed space for this parameter, you use hyperparameters, okay?
Can I have a question?
Yeah.
How do you know you're not overtraining those? So let me give a very cynical example of this. So I have a black box learning something that I want to produce. Internally, it's going to do a random number generator coin flip, true, false, right? Okay, something. And I wish it would produce true, 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 right? and my hyperparameter is the seed of my random number generator. So then I'm doing my research, I keep changing the seed. Oh, this seed, like, it's only 50% true, no good. Okay, let me keep changing the seed. Okay, after a lot of tries, 2 to the 1 over 2 to the n tries, I find a seed for which I can get 10 in a row, true. Right, and I've now tuned the hyperparameter that I have access to give me all true. But what I really have inside is a random number generator, right?
Yeah.
And so, like, I don't know if I'm being clear in the description, but like somehow you have control of these magic things you don't really understand what they're doing. And you're getting different outputs. And now the question is, how do you know you're doing anything sensible?
Because you can still evaluate. There was, so if you your objective was to do a random number generator, right? In the real evaluation phase, you want to be able to have true, false, like you want to have both, not all trues. So even if your training case ended up resulting into all truths, when you take it to the evaluation case where you're not using that fixed set coming in, it will show a different answer. So now your performance on that is not good enough. So what I'm describing is more of like a supervised approach where you have a result in the evaluation set as well. But in terms of random number generator, your evaluation can be the standard deviation between your data set, and if that is 0, then in case of all true, that is going to be 0, then it's not optimized. Okay, so any questions on hyperparameters? Okay, the next stage is train and optimize, which means you have your data, you have extracted features out of it, you build a model for those features, and now you need to combine the model and the features. Features is the data basically, but you need to combine them. You need to train this model using the featured data coming in and train it and keep updating the model, right? So the model once built needs to be trained. Training is the process where you're updating the parameters. As I mentioned, parameters really are your model. Like they are the ones controlling the model. A model has an architecture and parameters. The architecture defines how these parameters go forward in the calculation. But ultimately, what is being updated are these weights. So if I'm, I don't know if I gave the example last time, but if you have a quadratic equation, ax squared plus bx plus c, a, b, and c are the parameters, right? If you know the equation, you know what a, b, and c are. When you are learning that, you want to reach close to your correct a, b, and c, right? How will you do that? You will follow some process to train your model to ultimately reach it. That you start with random values of a, b, and c. You start showing it data that x goes in, it follows the process, and then y comes out. Do I know what the result is, right? So sort of this process, keep doing that, keep updating values of a, b, and c. And if you were able to learn something good, you will reach to the right values. You will reach at least very close to the right values. So going into the training process, you need to have an objective. So you want to learn the parameters, right? But how do you really learn those? You have to have a definition of something which is called as a loss. Take it this way, like there's an objective that you want to achieve a target and you want to minimize the distance between the target and the reality, right? Because if your model, what the model is predicting, if that is same as the target, then your model is good. But if that is really different from the target, then you haven't learned a good enough model. So this distance between the two, the distance between your prediction and the target is what you're trying to minimize in the process, right? And then you need an approach to do that. To how do you really minimize? How do you update your model parameters? What is the criteria that will be used to sort of keep updating the model, right? You will use a certain update algorithm. In the backpropagation is one big example of that. But what is it? What is really happening? Backpropagation, neural nets. These details I'll cover, I think, in next week. But to get an idea, just assume that backpropagation is an algorithm which knows, given a loss, how to update the model, right? So you have an algorithm where once you have provided it the target and the prediction and the distance between them, which we refer to as loss, you are able to update your model. Okay. And this process is then iterative. What happens is that you will perform this step. Let me just go over this quickly, and then I have a diagram to explain better. That the process of updating these parameters is iterative. That you're going over the data set, updating the model, then going over it again, updating your model, and so on and so forth. You are sort of updating it in steps, because in most of the models, you cannot just come to a good conclusion in the first run. You have to keep on updating them, and then depending on this new value that they learn, they know the direction in which they are moving. So the way I'm describing it is more of like gradient descent, which is one of the approaches. But in different algorithms, you can follow different iterative processes. The core idea is you want to reach to the best parameters by continuously sending your data and comparing the loss, right? So comparison of predicted values with the ground truth provides a certain loss. Then you use the loss with a certain criteria to update the model, and then the data is passed through it again. So what happens is that you first do a forward pass. This is your first step. You have your data, you pass it through your model. Start at the beginning, your model may have some randomized parameters. Okay, so it will give a response, it will predict something, but that prediction may not be even close to the correct. So you have the predictions, you will measure a loss. No matter what those predictions are, you can always compare them to the ground truth, because this is describing a supervised learning process. We'll mostly keep on working with supervised learning. I'll explain how to deal with unsupervised learning processes later on in the class. But for the sake of this class, applying ML, we are sticking mostly to supervised learning. So forward pass through the model, you reach to the predictions, you gather a loss. How are you getting the loss? You know the truth and you know the predictions. There are different methods to do that. You use one of those functions and you derive a loss. Now, what do you do with the loss? You know the difference of your model with the reality. Can you use it in a smart enough way to really update your model? That is the final stage of updating the model, where we have a criteria using which we update the model parameters, and then we have a new model in a way, or an updated model. The state of the model has changed from purely random to slightly informed, and you do that again. It becomes more informed. You do that again, it becomes more informed. And at the point when the loss is really low, you will sort of converge, because your loss won't be high enough. You will have the model parameters at a state that they cannot really update more to improve themselves, and you have your best trained model. This is not by definition an automatic process. In most of the cases, you are sort of hard coding the number of iterations that you will be operating on. But there are some methods which I'll provide reading links on, called like early stopping, where you are at every step sort of doing a validation measure that, is it good enough? Is the model good enough yet? Can I stop? Because you don't want to overfit. If you have a well-defined structure, you will prevent overfitting using some methods for regularization. We can cover regularization later, but you can control overfitting in a certain way. But there are also methods in which you can control how much to do, how many times to iterate over this. How do you control the process? Like early stopping is one of the most common. So looking at this, is this cycle clear? What is the iterative process of training a supervised learning algorithm? So can anyone just run through it once?
What you just said.
Yeah, what is the process exactly?
And this is this work for pre-trained models, or this is not? This is training.
You're training a new model.
If you use a pre-trained model and only train like a couple of the layers, like tweak it,
Yeah.
Do you go through this?
Yes. I mean, for those layers, you're going through it.
Okay.
You're treating the other layers as a function, so like a mathematical operator, right? So yeah, I will cover that portion, I think, in some week 5 or something, which is called transfer learning, where, as you mentioned, you have a pre-trained model and you are just training some portion of it. Means you're not using your data to train all the parameters, whereas it's a large enough model and you have some parameters which you still want to train more for your problem maybe, but the remaining ones you just want to use them as pre-trained. Like you got them from somewhere, they work really well for certain cases, and you don't really have enough data to improve them by yourself. You use them as a mathematical function instead of training them. So is this process clear? What is happening in the training round? Okay. And one more step before you move on to evaluation is validation, which means you're not checking the results on your test data. You are keeping a small sample of your training data set itself, which you don't use in training, and use to validate. So this is something that you can keep changing in your different training rounds, not in different epochs. Epoch-wise, you retain the same, but before you really say, okay, I have a trained model and now evaluate it, you can do several rounds of validation. Validation means a small sample of data, which was not a part of your training data. So when we entered into this process of forward pass, you did not send that data through this process. But once you stopped, so once this round was completed, you performed a step of validation. So before going on to it again, you performed a validation and you derived a score. You derived a value of this loss. And you're saying, if this loss, over here what you get is a loss on your training data, which is being used to update the parameters. When you perform a step of validation, you're getting a loss on your validation data, which is not known to the model at the time of training. And you're saying, so that's unseen data in a way. And you're saying, give me the loss on unseen data. If that loss is really low, is lower than what I really wanted it to be, we are good, we can stop the process, right? That is a good approximation of a complete, of a good learning process. So instead of waiting till the end of your iterative process and looking at your test data, you're also doing an evaluation while training so that you can control how much you want to continue. Mm-hmm.
So wait a minute, so this is all of my data.
Yeah.
I take maybe this much for training,
Yes.
and then my validation data, each time I validate, do I use the same fact?
Mm-hmm.
Or do I use part of it and then?
No, you use the same. The thing that you said, you take a part of it and put it back in, is called cross-validation, which is another thing you do for sort of validating your data set. But that can be done with the test data also. When you're publishing your results, when you really want to show that your model works well, one random split is generally not considered to be a good enough measure, because maybe it got randomly split into a way that you got really good results. But can you do this many times and see if it works well on both, on all those cases? If I split my data randomly at different places, will it work well? So that's called k-cross validation. You build it, you do it into k splits, and you are using one split at a time as your test. K minus, so one as test, k minus one as trained, and keep on doing that. But in a normal validation step, you are just taking in a small sample, which will be used to evaluate the performance. The idea is to test the performance of your model on unseen data, because it may be overfitting to your seen data. So great results on training data are not enough. As I mentioned like last time.
Yeah, but each time you validate, you're using the same data.
Yes. Okay, so this is validation, and hyperparameters can also be tuned at this point, because if you're not seeing good validation results, you may want to update your model and train it again. In very small models, this process doesn't seem like much of a thing, because I mean, how long does a logistic regression generally take? Not much. But when you are training really larger models, if you don't have validation, then you are just sitting there for days waiting for it to get over and then show the results on test data, which just isn't a good idea at all. So validation becomes a much more important step, because in object detection, there's a model called like YOLO, you only look once. It's a large model, and one epoch takes more than a day sometimes, depending on the GPU that you're using. But these are really large models, so you have to perform the validation step. Epoch is the term used for number of iterations. So each iteration is in each epoch. That's okay. And so any questions in the training and optimization part? Okay. Now we move on to the final part of the pipeline, which is called evaluation, which means you have your model and you want to see whether it works really well on slightly larger unseen data. So validation data set was very small because you want to use as much data as you can for your training while also being able to evaluate. So you make a reasonable split, but not too much. But for test, for really claiming that what you learned was valuable enough and it was generalized learning, and you can show results on a still significant size of data set, use a test data set. So in last class I discussed, we are splitting the data into train, validate, and test. This is where you use the test data set. And absolutely unseen data, there cannot be any matching between, basically no sample from training data can appear in your test data. Otherwise, I mean, you're cheating essentially. So your model has to be validated on completely unseen data, and then the performance that you get is a measure of how good your model is. And you do this for different models, for different applications. You do this again with different hyperparameters, but these are the final results that you get. Once you have a well-trained model, once you're satisfied with the results that you get, you put it into deployment. So for publishing a paper, you stop here. When this goes into real practice, you had your data, you had your splitting over there, you had your train and test, and it showed great results on test. But unless that result really translates into real world result, the model is not much of a success yet. So A/B testing is one of these common processes that are practiced in almost all the companies now, which means, so most of the companies right now, their products are provided to you as a service, right? So you have Gmail. Access to Gmail is provided through a Gmail server. Their server is providing the product to you, their server is providing product to me. And at the same point, they can choose to vary the product that you and I are seeing in terms of some updates that they might be trying, right? So if they have an updated product, let's say they tried a small update, they built a new learning algorithm, the algorithm they use for autocomplete of your mail. If they want to deploy it right away, no matter how it works, every user will have to use it, right? So that's not the way to go. The way to go is that you try it on a small percentage of users and you keep on analyzing their usage, right? And you have some metrics that you define for your use case. So these metrics are not standard metrics. These are your product specific metrics. For Gmail, it might be the number of emails responded in a day or speed at which each email was being responded, right? So you train a model which works really well on your training data, test data set, deploy it in the real world, and then serve it to a certain population or a certain percentage of your users base, and then keep deriving the performance metrics, and then you do a performance check. Did the usage improve or did not improve, or did it worsen the usage? If it improved, what was like how much did it improve? So training has a certain cost, right? Is the improvement matching the cost, right? Is the improvement big enough that you train this model, or maybe it's not good? So the impact that your machine learning solution has actually created needs to be evaluated, needs to be validated from real world performance. That is the stage where A/B testing takes place. In industry, you have to do it. In real world products, in real world projects, like this course sort of aims at, this has to be the approach to actually understand whether something is working. You get a data set in the beginning and you try to learn whatever you can from it, but that is never a final answer of whether the solution really makes an impact. You want to have a continued testing, which is generally in the form of A/B testing, but you want to sort of keep on evaluating whether the solution is making a difference, right? So,
So I understand A/B testing in general. I'm
Mhm.
having trouble understanding its context in machine learning. So maybe I'll be able to give an example which is better, but I'm thinking, okay, let's think about that cucumber farmer, right? I train a system that's going to automatically pick my robot to do something, right? I don't have an alternate. I trained something, I stuck it there. So what's my B?
The alternate is not using it, and
It's
you
the
can't,
person.
yeah.
basically, so let's say now you have two farmers. One is using it, another one is not using it, right? That's your A/B testing. The one who is using your method, is their outcome better ultimately than the one who is not using it? So is the solution even worth something? This is the,
So that's super expensive if your B is don't have an automated method.
Yeah.
Right? Like if I compare to like Google is doing A/B testing on their web pages, right?
Mhm.
Like it's not feasible to say like we're gonna let a human look at every click on those pages. Like I believe though, right? Like you're gonna right? I guess you can change like your fraction of A and B, but I normally think of A/B testing as like I've got two automated things.
Mhm.
Right? I don't know. Okay, but anyway,
Yeah,
but if you're,
mostly-
so like, do you have an example of like machine learning where it would be like this?
The-
Do you think of it as like your old machine learning algorithm or your
yeah,
predictor without machine
many times
learning?
it's old, but in the case of the Gmail response thing,
Yeah.
like now when you start writing your email, you already have these things that start filling out
Yeah.
as you're adding text. So there was a phase when they must have tried it on some users and not on all the users. I mean,
Yeah, right.
right? So this means that there was no learning solution. Maybe there was some, but at least there was no autocomplete machine learning solution, and they introduced it. So now they are seeing whether a user without that solution is using it in a better way or not. And I think in Gmail in particular, I've seen so many features coming in and going away. I think it's heavily using A/B testing. So yeah, so that's A/B testing, and that's the entire process pipeline. Next, I'll go over a real data set and how you can do this in Python. So basically an introduction to what you're doing inside. I think it's time to take a break. So what I did was I sort of found a data set which helps understand some of the this pipeline, as well as relates somewhat to a social problem. I mean, it's not related to a big social problem, but I mean, it is a big social problem, but it's not related to one of the global goals directly. This problem is that, toxicity in content. So communications currently, like forums, there's this big idea of hate, and people are just writing a lot. There are a lot of hate comments on social media. So Kaggle hosted one challenge. I think it was funded by Google also, about toxic comment classification. So they have described, let me open the challenge. So what they have described over here in the data is there are these 6 types of toxicity levels, which they have. These are the labels basically that they are associating with a piece of text. So some comments may not have any toxicity at all, but some may have any number of these toxicities, right? So the idea is you get a piece of text and you have certain labels associated with it. The way this works is that you will get the data set in a CSV file, and Kaggle in general, first I'll go over the data, but how I can explain Kaggle in general is it is a great platform if you want to find good data sets, even related to your problems. So they present data sets mostly in the form of competitions. They also have data sets, but those are fairly small. Those are, if I find a data set and I want to upload it, I'll go and put it over there. But the real large data sets are available in competitions.
So you just pretend like you're gonna compete with the data set.
If you are competing, if it's an old competition and deadline has passed, you just use it as a source of data set. So there are two phases of a data. Basically, this competition ended a year ago. So yeah, now this is just a data set available for you to practice or for you to compare your results with whatever was the best. You can use the best results here as benchmarks for your algorithms and try to build new algorithms. But in terms of being a repository for datasets, this is one of the best available right now because there are some more. I will add links to those as well. But 4 years ago, I think UCI was a bigger repository. Now, absolutely, Kaggle is one of the best repositories that you have access to. In terms of social good space, there are some data sets on Kaggle as well, which can be used to build at least some learning component. They may not directly relate to your problem, but maybe they will be useful. But in this case, what we are doing is we are looking at this particular challenge about toxicity. We will figure out how the data looks like, and then we'll go through a process of data gathering, feature extraction, and everything, right? So the way these competitions provide you data is in the form of, generally, that's how they provide it, in the form of a CSV file, which is a comma separated value file. And the way this train file looks like is that it has these columns. So an example is this. It has an ID, it has some text, and then it has labels 0 or 1 associated with all the 6 toxicity types.
And can they be under multiple?
Yes. Yeah, so this is an example of, which kind of classification is this an example of? I covered like 3 kinds of classifications in the previous class.
Multi-label.
Multi-label. Because for each and every.
But I guess, but could it be under toxic and severe toxic?
Yes.
Or okay, so but it sort of seems like if it's categorized as severe toxic, it have to be
It will
toxic.
have to be that may be true, that may not be true. Something which is an insert and I don't know, maybe,
So something could be definitely be an insult,
but not, yeah. So
But okay, well,
there are these possibilities, right?
Severe toxic. Severe toxic has to be a subset.
So that's just an example of a data set, right? Now, this is text data. How do you really start with text data and perform a full stage of classification, right? So we move on to a notebook. Everyone here has installed Python at some point on a machine. So I was first thinking like maybe I'll go over some of those pieces of how to set up an environment and everything, but then they just consume a lot more time. So I will find links to good enough resources. If I don't find something, I'll probably create a small post of like some of the main steps to deal with it. But the assumption is that you will be able to set up a Python environment on your machine, which has the required libraries. Once that is there, let's start a notebook. So we are going to start something which is called a Jupyter notebook. And let me expand it a little bit. So I have already created this notebook and I'll go over it one by one while running through it. So a notebook, this is running on my own machine. A Collab notebook looks almost the same way, slightly prettier, but is running on Google backend. Okay. But the underlying thing is still an IPython notebook, which means you can write Python on it and you can visualize the results going into it. So first I just load some important libraries. And now the process of gathering data. The data was provided in the form of CSV files. There was a file called train.csv. We download it, and now we want to read that file. We want to see how that file looks like, right? So what I'm doing over here is I'm just taking sample 100 rows, but you can remove the sample size or you can just take a really large data set. I'm doing it so that everything is very fast over here. But this first step, pd.read CSV. PD is pandas, which is a library in Python. This library is great for data analysis. There's a language called R, which is a language used by statisticians dominantly for data analysis. Pandas is sort of Python's library, which gives you, I think, a large number of capabilities of R. So I haven't used R particularly, but for data analysis, I use pandas. How it looks at your data is that your CSV has a large number of rows and columns. It allows you to look at your data vertically and horizontally at the same time, right? So vertical, basically column in a columnar way. If you want to perform an operation on an entire column, it's very easy with pandas. So by doing this, what we're saying that we know that this file is already in a CSV format and just read it. If the file is not that clean, there might be a pre-processing step that you have to do. But for this case, I'm using already a clean already a clean file. We load the data and then we just sample 10 elements out of it. And this is what the data looks like. Every row has an ID. It has a comment text, and then it has these 6 values, right? These values go between 0 and 1, and every time I sample, I'll get something else. So this time we got some one with, so let me just sample with more 1 variants. Yeah, so this may be a case where we have toxic, we have 4 labels here, 1 label here. So it's going to be a case of multi-label classification, but that's how the data looks like. Let me actually just do one more to remove that last comment. Okay, so up till there, we have our data. We gathered the data. Now we want to perform feature extraction on top of it, right? This part is clear. You get a data set and you load it in a certain understandable format. This thing is called a data frame. So now you will do feature extraction. So you have a large number of comments. You want to sort of convert them into a format that can be understood by a classifier, right? So there are different ways we can do it. I also introduced in last class 2 ways: sequence indexing and the count vectorizer for parsing text, for using text features. We'll be going over the count vectorizer. I'll explain again what it is, but the first thing that we are doing over here is more.
Yeah, it's pretty little.
Okay, let me do as much as possible by the screen. Okay. All right. So now we have, this is the first step where what I'm doing is I'm taking in all the comment text. I'm taking that column and just creating a list of all the text. Because in order to understand my entire data corpus, I want to sort of work at this vertical level first. I cannot just go sentence by sentence and say, remember, like we have to define a vocabulary of the space. This is our step to define a vocabulary, because now we know all the words, all the sentences, and we are treating all of them as a documents. And this is just visualizing 5 of them. And now, generally, they contain a lot of things. So over here, see, this is a \n, then there's no space and dot and different things. So there's a process which is known as tokenization, where you want to extract words, useful words out of this, and you want to do a certain kind of cleanup. In this case, we'll do a very tiny version of it, but depending on your data, how clean it is, what kind of data it is, you can do several kind of tokenization. Like for example, for a tweet, there are a lot of @handles, right? A tweet can have, it can use a large number of @handles, it can have a large number of hashtags. So you may want to extract that piece of information differently, and you can apply tokenization, which takes care of that element. Whereas in the normal text, you just want to, let's say, split at the space, so you keep getting every word, or you want to split at space, comma, new line, full stop. So these kind of things, different kinds of tokenizations. For the simplest case, we'll just deal with space. But up till here, you are just collecting all the documents. Now you want to clean those up. So now For cleaning, we are using another library. It's called NLTK, Natural Language Toolkit. This is a Python library most dominantly used by people working in natural language processing. It has a large number of pre-built tools. So over here, what we are dealing with is stop words. And what are stop words? It's just the set of words which are used very commonly. So these are not the words on which I want to sort of base my classification. These might not be the words. If I'm trying to learn language, I want to use all the words. But if I'm trying to learn that my intuition going in this is that if I want to build a very simple model, let's say, if there are some kind of words that exist in a comment, this might be toxic, right? It might not be a good enough assumption to really learn which kind of toxicity it is, but let's start with it. It's the simplest model. So for that, we are removing at least these stop words. We are saying that now the moment at which I'm going to vectorize each and every comment, when I'm going to extract pieces out of it, at that point, I'm not using these very commonly occurring words. They don't hold any value in my evaluation. They just appear in every sentence and they're too common. So these are called stop words. Now, can anyone explain this line? Any Python user? Yeah.
So for every comment, every set of comments, you're gonna take all the words, you're gonna split out the spaces, and you're gonna turn all the words to lowercase if they're not a stop word.
Yeah. So now we are converting each and every comment into a list of words. But while doing that, what we are saying is that first of all, turn all the words to lowercase. Don't keep a variation in uppercase, lowercase, or any mixed case. And split the words at the space. Also, if that word belongs to the stop words list, don't use it. Now every sentence is reduced to this kind of list of words. So you can see that like the first word that the first sentence that we had over here, this explanation one, is now a list of these words, right? So
what is the side of stop? Stop would be some words that consider stopping the whole English vocabulary.
yeah, so see over here, stop words dot words from English are the extremely like the commonly used words in English. So you can see I, me. I can show you some more. That's it. 30. So I, me, myself, we, are, right? These are the commonly used words. So you.
So somebody else created that list.
Yes, that's the beauty of NLTK, that there are many such lists, which if you want to create yourself would be an effort, but if you use a good library, you have access to these things. Similarly, they have very good tokenizers. Like the tokenization is this thing, comment.split on underscore. That's how I am tokenizing my sentence. But in a sophisticated process, I would use something called tokenizer. NLTK provides tokenizers, and then they have a certain number of criteria on which they do it, like regular expression, or there are more. I remember using the regex one, which would do a much cleaner job. So over here, you can see that this became one word now dot something, right? I also did not clean the \n, whereas I should have cleaned it. So there are.
So if you wanted to clean that, would you just put it in the out statement? Would you add to that out?
Where?
To that list, you know, you stop words from English, because you also have, could you say stop equals stop words from English plus
\n? No, because
no.
there is no space between these. There is no space over here, because that could be my criteria for splitting. Right now, I'm splitting on a space. So if you say \n is a stop word, this word is not \n, it's explanation \n y.
Okay.
Right? So you have to, instead of this one line of tokenization, you have to have multiple lines, like maybe comment dot replace \n with a space and then split on space, and we can just do that and it would clean, like comment dot space backslash this with the space, and then now the statement that you get, you replace it. So okay, so explanation is correct now, right? And now it removed y because y was the stop word. So that's just one more step in the tokenization process. Okay, so at this point, from just a sentence, we are down to a list of words, a list of reasonable words. Now we want to build a vocabulary. So the process of building a vocabulary can be manual, or again, you can use some great libraries that exist. So we just, and I will be providing this notebook, and you can use it on the cloud. So video is not really required. You can import this library, Gensim, helps translate your text into dictionary. We can do a manual process as well. The dictionary is basically an index of all the words that you want to deal with, and then you may want to keep some more information around that. But the idea is that it's an indexed list of all the words. So using this library, you can, once you have your text in this format, list of words, you can just do dictionary, and then it has a dictionary of 2337 unique tokens. Because it's a good built-in function, you just use it, and then it has some more properties. So 2337 might be good enough now, but there is one more cleanup step that we can do. We can probably remove words that occur too frequently, because they may not be adding value as well. So that's one step. Like, we can do a frequency-based filtering. So Gensim provides us with the function that dictionary.filter n most frequent. So we are just removing the top 20 most frequent numbers. So it had 2337. Once we do that, it has 2317. That's one level of filtering. Usually it's fine, but if, let's say, we have array, so this is just 100 samples. If we had really worked on the entire data set, the vocabulary would be huge. So now we want to remove a lot of words which are just maybe, let's say, occurring one time. They are going to be a large number of words. They might be names, right? Names of people, which are occurring once, twice. And if it's a really large data set, you don't want to care about those words. So how do you clean those up? There's an extreme filter, which removes, which has this criteria that no below means words which are not even appearing 2 times. Remove those. And no above means words which are appearing in more than 99% of the documents. You have 100 documents, you have 100 different comments. Words that appear in 99 of those, just remove those.
Is that just assuming that they would be link words like the or and or but?
Yeah, words that were not in the stop word list, but maybe they were important words in the, if our comments are from Twitter, right? Stop words will, and you remove the stop words. There is a thing called RT, MT, right? Retweet, mention tweet. People often have RT in a large number of tweets. That's not a useful word for my learning, but it appears in a large number of documents. Maybe it appears in more than 50% of documents. How do I get rid of those words? You can build a manual function also, but this one really works well. So because it has these kind of properties. So by default, it's set to 5 and 0.5. Like, if you have a large enough data set, if something doesn't even appear 5 times, and if something appears in more than 50% of the documents, it removes it. For our small case, I've just kept it to this size. Okay, so now we have our dictionary limited down to 422 words. So vocabulary is done. Now, how do we, and our comments still look like a list of words. Now we want to convert them into integers or some representation which can be sent to a learning model. So we transform the data using another function by Gensim, which says, does anyone know what this means? DOCTBOW, DOC2BOW. No one? Okay, so it's just basically doc is understood, right? We are dealing with a document. at a time to document 2, and BOW is bag of words. You have a vocabulary and you're now trying to say, okay, this document is a bag of words where what the key is the word, is the index of the word from my vocabulary, and value is the frequency. So this one says that the first sentence, if I look at it, is a bag of word where dictionary, the 0th word from my dictionary appeared once, first word from my dictionary appeared once, and so on and so forth, right? Because it's the first document, it has the 0, 1, 2, 3, 4 thing. But going down, you will sort of observe that different documents have different frequencies of values. Yeah. The frequency. Yeah. So first is the index, second is the frequency.
And it's the frequency just in that little word, or frequency out of the entire.
Doc to BOW. Each document is being transformed to bag of words. So now this corpus, if I want to look at the length of my corpus, what is the value that I should get? If this corpus is basically each document translated into bag of words. So how many elements should be in the corpus?
2,000. 2,000
The number of data samples, right? Yeah. So this is basically 100. So what we are dealing with over here is this dictionary bag of words representation of each and every text. So from the normal text, we went down to a list of words, and now we went down to this key value pair, where key is the index in a standard dictionary, which is common for entire data set, and value is corresponding to the document, right? So
each element in corpus would be the dictionary containing all the words, or containing the unique words, and it counts for each.
for the word,
document.
yeah.
And
Sorry, can you repeat?
so the corpus would be a list of documents, right?
Yes.
And each
Document.
list, each sub-list has the dictionary of words in the whole dictionary, in the whole vocabulary in its appearance.
Yeah, so a document is a dictionary in this case now, right? Where the key of the dictionary is the index of the word in your vocabulary, right? So the key cannot be from outside that vocabulary. And the value is the frequency in the sentence. How many times did some word appear in my particular sentence?
In that sentence.
In the sentence, in that comment.
Okay.
So entire comment, not just sentence. Right? We can do a quick example, I
Well,
think.
where are you, I mean, okay, so I'm being stupid, I'm sure, but, okay, so if we just go through what you have there, the
Mhm.
very first one that you have,
Yeah.
you have like the 0th index,
Mhm.
right? Occurs once.
Yeah.
But that same, whatever that index is representing, whatever word that index is representing, that probably occurs in other texts,
Yes.
right?
Then they will have a 0, whatever
And then
frequency.
it'll show up as a 0 further on, like one text.
0 is its index.
Show an example. Just show an
Ah,
example.
okay, I
Okay.
just saw it. I hadn't seen that. Sorry.
Okay, so see,
Okay, that's.
this is our first sentence, right? Text 0. And this is the bag of words representation. For
Right.
the sentence. What it says is that,
So there's no.
let me actually print one more thing to explain
No,
this.
that, I got it now.
Mhm. Just a sec.
So like the first sentence started with a the, and it was on my stop list. And the third sentence started with a the. And if the was only once in that first sentence, it would be 0, 1.
Yeah.
And then down to the third sentence, it would be 0, 1 also. And
Yes.
then every single sentence that had the,
Yeah.
you have a 0, and then
And
the
the number of times it
those in
has
that
the, exactly.
And you're creating a fresh dictionary.
The dictionary,
I previously thought you were pulling a dictionary that was known.
no, that was, yeah, dictionaries for the data set, what we are making.
Because I'm seeing, this E9, blah, whatever, right? Like that's coming out of the data set. That was-
Exactly. So what we loaded was just a list of stop words, right? So up till here, is it clear? Like so from the comment we went down to a list of words, we went down to a list of clean words, and now we went down to a bag of words. Still not good enough for a general learning model. I mean, if you can translate anything into a vector, that is how we really need it. I mean, a vector goes in, and the model is going to apply a mathematical operation on top of it. So now we create sort of a feature vector where what we are going to say is we had 400 something, 422 words in our dictionary, right? This is what we finally had. So now, instead of doing this bag of words representation where I have everything in a variable length, right? Every sentence will be a variable length. I want to make each and every sentence to be of same length. How can I do it? I can have each and every sentence be represented as a 422 long vector, right?
Okay.
And the position in that vector is the key. The value in that vector is the value. You see that my
Yeah.
point over here?
So each one is 422.
Yeah.
And but
With a large number of zeros,
okay, right.
Yeah.
And then wherever it is.
the frequency.
Right.
So you are creating TF-IDF
No,
representation.
not IDF. TF.
No.
This is not IDF.
Okay. Just.
Yeah, this is just term frequency,
Okay.
right? IDF would have like an inverse document frequency value, which will reduce down the importance of words which occur too many times. But right now we are just doing the term frequency. Just so that's why I use the term count vectorizer for it, that you're just vectorizing on the number of counts for each and every word. So the vector, the 422 size vector, is now a fixed vector with fixed words on the positions in your dictionary. The index of the word in the dictionary is the position in the vector, and it will basically create sparse vectors.
Okay, so when we do that, with each of these individual ones, I can tell not only the frequency of the word, but I can tell
The order,
the order that
Yeah,
it appears. But with
the order was not available in bag of words as well.
It wasn't?
No.
Oh, wait, because the could have been
Exactly.
further on.
Yeah,
that's
but
very
that's a good point. So in this simple model, we are ignoring one critical piece of information. We are not looking at the order in which words appear.
Right.
We are just, so a sentence written this way is same as written this sentence away or whatever, right?
Exactly.
So there is no difference in the order of words. And in natural language, that's a really important piece of information. But if your model works well without knowing that, works reasonably well, at least better than random probability, you have something, right? You have something which you can deploy, at least to improve the situation. So ignoring the order information, we create this sparse vector. How it looks like is this, right? A sparse vector.
And the frequency is just within one comment. There's been
Yes.
turned into a list.
Yeah, so this thing that we have is equal to the number of data points. Each row is a comment, right? And each comment is represented as a 422 size vector with the values being the frequency. And just to give a test that whether it's frequency or just ones, it's actually frequency because the maximum value is 11. So there is a sentence where some word appeared 11 number of times.
No, that makes total sense, because from each line, you could recreate your backwards
Yes.
from each line.
Yeah.
That makes.
Okay, so the entire bag of words is in each, so it's being compared to each comment.
Yeah. Each comment is using all the words.
There's a bunch of zeros.
Right, because the bag of words is all of the possible words.
So
Yeah.
the bag of words is just whichever words you found in that sentence, and that one
I don't see
is
why we need
all the
bag of
words
words.
that you could have
Right?
found.
I don't see why you need a bag of words. It's just an
You see
intermediate
what I'm
step.
saying?
The bag, I thought that the bag
I
of
only care
words
about
is
the
400.
vectorization.
Yeah, you only care about the vectorization, but you needed the indices, right, for the back and forth. Those indices, you reach to them using that step.
Yeah, this is just because you have to have library functions that make it easy to do.
Yeah, exactly. What you really need is just
I'm
that.
not using the bag of words for anything, right? Like if I had a function
Yeah.
that directly was in my dictionary,
Exactly.
it's like this thing in the dictionary.
One more.
Ultimately, that's the representation.
Okay, so in the big thing, it would be 1, and all the zeros, but then later I have I, really hard, and that's 0, not with the 1 or 2, but the 3 and 4, it'd be 1, it'd be 0, 1, 1, 0, 2, 0, 3, 1, 4, 1. Do you see what I'm saying?
there's
And so
an
you
I
could
and then there's a
reconstruct it, yes, you could reconstruct it. Just by taking out all the zeros, you would have that same first thing that he did. Just take out all of the columns that have, take one row, any place there's a zero, ignore it.
Mhm.
It had to have one or.
And then you just take,
have the-
you're going over the indices, take the index as the key and the value there. Okay, so that's the
But you
main.
cannot go all the way back to your clean comments from here, right? Because you lost your order.
Yeah,
Right, right,
order
right,
is
the order
lost.
is
We cannot go back to clean comments from that.
Seven.
So we can only go back to bag of words. That's it. And we can describe that as a bag of words in terms of the real words. That's what we can do. Okay, and then so now we know what's going to be the feature vector going in. We need one more thing, which is the output, right? Because a model needs, it's a supervised learning model. We need the input going in and the output coming out. In this case, it is very simple. They're all numerical values. You don't need to do anything. So from that large data frame, I'm creating a small data frame which just contains these 6 columns, right? So it's indexed correctly as the same thing, and you see this is how it's looking like when you have all the numerical values. Converting it into a matrix is really simple.
Wait, so
Can you run that
hold on.
again?
For
I got a bunch
that,
of zeros.
I don't-
Is that
Yeah.
Random.
Yeah, it's sampled 10. So
Okay.
see, there's a 1.
so wait a second, what's the 18, 16, 10, 54?
It's the index. Index in, so since I'm sampling 10 elements, my data frame had 100 elements because I loaded 100. Now this is a sample. So it's just showing what index it is.
Ah, so the 16th comment that you had one top.
Yeah, exactly.
And here's a question, did somebody look at those 100 comments and pre-label them for you?
Yeah.
Or, yeah, okay. So-
I mean, that's why you have
Or
this.
did you have a list, or did you have a list of words that when you sampled, it said, oops, that's one of the words, I found it on
Yeah,
line 16.
then then you have a B classifier classifying your content, right? Then it's not really a good label to use. So this is another important thing actually in real world situation. How do you label your data?
Mhm.
So one idea is to get crowd labelers, like crowdsource the process and have human labelers label them, and maybe have a consensus on top of multiple labels per item. But there are different ways of labeling things.
But after you've trained it with the human label data, then you don't need humans to label you. Then like the computer can evolve and
Yeah.
identify.
Because you're assuming that the learn process is good.
Right,
Yeah.
right, right.
You go into A/B testing, it didn't work. You find more human labelers, right? So now the targets is represented as a matrix of size of shape 6, right? So these things, they are in the form of, when we vectorize them, they are in the form of a numpy array, n-dimensional array. And this is in, like, this one has a size of 106 because 100 elements, each element has 6 values corresponding to the labels. And now we are just going to do a quick train test split. What we are doing over here is, from those 100 samples, we are taking randomly splitting them into an 80-20 block and creating 4 different matrices. One matrix is my training features, another is training labels corresponding to those, and then one is test features and test labels. So this portion is just doing that split. I think again, developing model and remaining steps, I'll go over them next time. But so far, is this more clear, like the process through an example? Okay. Tomorrow, 11:59, tomorrow midnight, the Piazza reviews are due. So whatever comments you have to post, please do it by then. I won't be reviewing anything submitted after that point in time. Then assignment 1, I'll assign it tomorrow. I will go over it, how to do it in the lecture on Tuesday. It will be similar. It will be a notebook. Most of the things that I have written over here, consider it a fill in the blanks for something like that. Like you're running through a data set, you're doing a process, but you have more of a, you have to write some pieces of code. And then submission will be through Crowd Creator that I will cover up on Tuesday.